Imagine asking a state-of-the-art AI to diagnose a really complex disease. You're probably assuming it's reading all the latest medical textbooks, cross-referencing genetic data, and, spitting out the perfect answer. But right now, across the entire tech world, AI is hitting a massive invisible wall. When it comes to answering these complex, multi-layered questions, even the absolute smartest models are literally crashing under the weight of their own memory. And why should you care about this? Well, we're increasingly trusting AI with incredibly critical, life-altering tasks. Everything from precision medicine to heavy-duty legal analysis. But simply feeding these systems more data to make them smarter is actually breaking them. They get totally overwhelmed, they forget what they literally just read, and they confidently fail even when the right answer is sitting right in front of them. But there is a breakthrough. Researchers at AWS and Cisco just published a fascinating paper detailing a radical new framework
that fundamentally changes how an AI agent searches and remembers, and in their best configuration, cuts token usage by over half, while rethinking how an agent searches and remembers. But it's not a universal fix, and the paper is upfront about that. We're going to dive into exactly how it works, and where it still falls short.
Section 1, Old RAG versus Agentic RAG. To understand the cure, we first have to understand the disease. Let's look at the problem these researchers were trying to solve. Think of the old way of doing things, which we call basic RAG, or Retrieval Augmented Generation, like a slightly lazy assistant. You ask a question, and it just blindly grabs the first 10 books that happen to contain your keyword, drops a massive pile on your desk, and kind of hopes the answer is in there somewhere. But the new way, Agentic RAG, that's more like a brilliant autonomous librarian. It maps out relationships, reads a little bit, realizes it needs some more context, and then autonomously decides exactly what to search for next. When you look at the architectural flow of how this works, the difference is night and day. Agentic RAG introduces actual tools and iterative reasoning,
Letting the agent think through a query step by step. And the paper's own data backs this up in a surprising way. Their leanest agentic setup, one tool, minimal instructions, outperformed every heavily engineered pipeline they built, including ones with dedicated query reformulation and re-ranking bolted on. Less scaffolding, better results. But here's where the problem starts. Because the agent is so thorough, it drags the entire history of its previous searches along with every new one. Researchers found this exact failure in their own logs, over and over. Bedrock through context window overflow error. In one case study in the paper, a single complex query needed 13 search attempts. 6 of them crashed.
Section 2, How Context Optimization Works. So how exactly do we fix a genius librarian that can't stop hoarding? Let's get to the meat of this explainer. Let's break down the agent's loop like we're 5. Step 1, the agent figures out what tools it needs. Step 2, it executes a search. Step 3, it reads the results and composes a new, smarter query. And finally, step 4, it decides if it has enough information to stop and give you an answer. That's the loop. But remember, doing this sequentially was exactly what was blowing up the AI's memory limit. To fix this, the researchers introduced a hero mechanism called batch agentic retrieval. Instead of the AI making a search, reading it, making another search, reading it over and over, they created a hybrid react-rewoo strategy. I know, sounds complex, but basically the AI now plans out multiple complementary subqueries right from the start and executes them all at once in a single batched call. This drastically reduces the number of those memory-hogging round trips to the language model. But they absolutely didn't stop there. What's really cool is how they cleaned up the memory itself. They introduced relation-grouped graph representation, which essentially compresses redundant data points. Then they used unified subgraph deduplication to ensure the AI's memory only grows when genuinely new information is found. And finally, they used content-aware document hashing to scan and instantly eliminate duplicate chunks of text before they ever even enter the agent's memory. And the results are absolutely wild.
In their best-case configuration, this cut token usage by 53%. Worth noting, across all the scenarios they tested, the reduction ranged from about 19% up to that 53%. The size of the win depends on the setup. Cutting the memory load did what it was built to do. It eliminated the exact crash pattern from the California case study. No more context window overflow errors. That part is a genuine, unqualified win.
So, problem solved, right? The memory is optimized, the crashes are gone. Well,
not quite. And the researchers' own follow-up data is the most surprising part of this paper. They pushed batch agentic retrieval to its limit on the hardest scenario in the study, the agent working with both document and knowledge graph search tools, batching their cut tokens by up to 48%. the biggest reduction they measured anywhere. But it also produced the worst accuracy in the entire paper, worse than doing no optimization at all. The same mechanism that killed the crashes, pushed hard enough, actively hurt the answers.
Section 3. The retrieval generation gap.
That failure is really one instance of a bigger pattern the researchers found across the whole paper, not just in that one batch configuration. Here's the cleanest illustration of it. In their most expanded retrieval setup, 500 paths, 20 entity subgraphs, the system successfully retrieved the right information 83.5% of the time, but the model only actually used that information in its final answer 47.9% of the time. Retrieving more relevant data did not proportionally translate into a better answer. That's the retrieval generation gap. And it's the same underlying failure that sank the batch retrieval scenario a minute ago, just measured a different way. So why does this happen? Basically, the model has a real attention deficit. The researchers confirmed the well-known lost in the middle phenomenon. If a crucial fact is buried too far down in the prompt, the model tends to just skip it. It acts like that information isn't even there. The researchers actually mapped exactly where the model was looking. If the answer sits in the first 10% of the text, the model finds and uses it 85.5% of the time. Move further down and usage drops sharply and unevenly, down into the 20 to 30% range at times. It's a noisy decline, not a perfectly smooth one, but the direction is unmistakable. By the 75th to 85th percentile of the text, extraction drops to 0%. Effectively, it stops reading that far down. But it's not just about position. The researchers identified 3 distinct causes for this gap. First, the positional decay we just covered. Second, semantic preference. The model favors familiar canonical terms over giving you an exhaustive list of everything it actually found. Third, query phrasing. Ask, what is a drug that treats X? And the model assumes you want one answer and will suppress other valid answers it genuinely found, even ones sitting in a high-attention part of the prompt.
Section 4. Real-world AI implications. So, what does this actually mean for the immediate future of AI?
Here's where I'll flag this as my own extrapolation, not the paper's claim. If this generalizes, it points toward coding assistants and research agents that can handle more complex cross-domain retrieval without crashing, as long as teams stay disciplined about how hard they push batching. But it also shows that retrieval-focused metrics like hit at K can overstate how good these systems actually are at answering. The field needs a shift in focus. We're genuinely good at fetching data now. The next frontier is restructuring prompts and building techniques that force the model to actually synthesize what's already been fetched for it, which leaves a pretty pointed thought to close on. We've cured the memory crashes, but fully exposed the model's short attention span, and shown that pushing the cure too hard can make the attention problem worse, not better. If feeding an AI more data doesn't mean it actually reads it, how do we architect the next generation to truly comprehend everything in front of it? That's the real question for the future of AI.